Welcome to subtopic 8.1, Theories of Acids and Bases. In IB chemistry, there are two theories of acids and bases that we need to learn. The first is Bronsted-Lowry, and the second is Lewis theory. Let's look at how they define acid and base. In Bronsted-Lowry, an acid is a proton donor, and a base is a proton acceptor. In other words, Bronsted-Lowry theory is just about passing around protons, the same thing as a hydrogen cation. In Lewis theory, an acid is defined as an electron pair acceptor, while a base is an electron pair donor. So again, we have acids and bases defined in terms of passing something back and forth, in this case, an electron pair. Let's look at Bronsted-Lowry theory. Here we have hydrochloric acid reacting with sodium hydroxide to give water and salt. The hydrochloric acid is going to donate its proton to the sodium hydroxide. After the sodium hydroxide receives the proton, it turns into water. Or more precisely, after the OH part of sodium hydroxide receives the proton, it turns into water. Meanwhile, the sodium and the chloride, liberated from their previous partners, ionically bond to each other. Now that's just a sideshow. The definition here of acid and base is in the green arrow, the proton moving from hydrochloric acid to sodium hydroxide. Here's another example with ethanoic acid and potassium hydroxide. Ethanoic acid has the extra proton. Potassium hydroxide will catch a proton. There's our proton that's going to move. After receiving the proton, potassium hydroxide will become water, or rather, the hydroxide group in potassium hydroxide will become water. In our final example with sulfuric acid and barium hydroxide, I'll leave it to you to see if you can follow the flow of the proton. I'll give you a hint though. The way I presented this reaction, there's actually two protons being transferred from sulfuric acid to the base, barium hydroxide. Now consider this example. Here we have bicarbonate reacting with water. The bicarbonate is the acid, and it's going to pass a proton to the water, which will act as the base. There's the extra proton on the water, which is now hydronium ion. Now look at this example. Here we have the exact same reactants, but now the water is acting like an acid and is going to pass a proton to the bicarbonate, which will therefore be a base. And there's the bicarbonate with its extra proton. Chemicals like this, that can act as both a base or an acid, are called amphoteric or amphiprotic, which are synonyms. Water can react with itself. And here we have water acting like an acid and water acting like a base, passing the extra hydrogen over, yielding hydronium ion and hydroxide ion. It's this equilibrium that gives pure water a pH of 7. Now let's look at the symmetry of all acid-base reactions. Here we have hydrochloric acid changing into chloride ion, and ammonia, our base, changing into ammonium ion. Of course, if we look at the back reaction going in the reverse direction, we have ammonium acting as our acid, transforming into ammonia, and chloride ion transforming into hydrochloric acid, acting as a base along the way. These matched pairs of acids and bases are called conjugate pairs. Our green pair, ammonia and ammonium, are a conjugate pair of base and acid, while our orange pair, hydrochloric acid and chloride ion, are an acid and its conjugate base. Here we have dihydrogen phosphate ion and monohydrogen phosphate ion, its conjugate acid. We also have ethylamine acting as a base and its conjugate acid. Of course, water, being amphiprotic, can be its own conjugate base and conjugate acid. Remember, we have two theories of acids and bases to learn. Let's compare the two. If we look first at just Bronsted-Lowry, and we use hydrochloric acid and sodium hydroxide as our example, there's our Bronsted-Lowry acid, hydrochloric acid with a proton ready to donate. And there's our Bronsted-Lowry base. The hydroxide group is accepting that proton. Now let's look at it from the Lewis point of view. The exact same reaction. There's our Lewis base. The hydroxide group has an electron pair to donate. And there's our Lewis acid. The proton is ready to accept those electrons. So the same reaction has the same acids and bases in both theories. Now let's contrast the two theories, and we'll focus first on the bases. Bronsted-Lowry, of course, says that a base must accept a proton, while Lewis theory says that a base must donate an electron pair. Here's our reaction again, but with only the core atoms involved. There's our Bronsted-Lowry base, the hydroxide group, ready to accept that proton, so hydroxide counts as a Bronsted-Lowry base. And there's the electron pair that the hydroxide group is donating to the hydrogen ion, so hydroxide counts as a Lewis base. If you think about it, anything that's able to accept a proton must have a free pair of electrons in order to do so. Conversely, anything that has an extra pair of electrons to share is able to accept a proton. So these two groups completely overlap. All Bronsted-Lowry bases are Lewis bases, and vice versa. But what about the acids? Bronsted-Lowry says that an acid must donate a proton, and Lewis says that an acid must accept an electron pair. Again, here's our reaction. There's our Bronsted-Lowry acid. The hydrochloric acid donated the proton. So hydrochloric acid is, of course, a Bronsted-Lowry acid. And there's the electron pair that the hydrogen ion is accepting. The hydrogen ion came from the hydrochloric acid. So hydrochloric acid counts as a Lewis acid. So for this reaction at least, it looks like the two groups completely overlap, where in fact, the Lewis acid group is actually bigger than the Bronsted-Lowry acid group. To see what I mean, let's consider this example. Here we have chromium trichloride, and it's going to combine with ammonia. Ammonia, where the central nitrogen has a free lone pair of electrons. When they react together, the chromium ion has accepted 6 electron pairs. So chromium trichloride counts as a Lewis acid. Notice no protons or hydrogen cations were transferred at all. Of course, the ammonia, though it was not accepting a proton in this reaction, all the ammonia were donating an electron pair, and they could have accepted a proton in a different reaction. So again, the Lewis bases are the same as the Bronsted-Lowry bases. So to summarize, the Bronsted-Lowry bases are the same thing as Lewis bases. Lewis bases are Bronsted-Lowry bases. And all Bronsted-Lowry acids are Lewis acids. But Lewis acids includes a few more things that are not in the Bronsted-Lowry acid group. That's it. Except there are actually a few more theories of acids and bases besides the two we've just discussed. There's an earlier theory called the Arrhenius theory, which was entirely dependent upon reactions in water. That theory was later generalized into the Bronsted-Lowry theory, which in turn was generalized into the Lewis theory. There's another theory that's not too well known, invented by a Russian scientist named Usanovich. In his theory, which is even more general than Lewis acid-base theory, an acid is something that accepts anything negative, electrons or a missing positive proton, whereas a base is anything that accepts anything positive, such as a hydrogen cation or a missing electron pair. This theory didn't take off very well because a lot of chemists didn't like that it was so broad it would also include all of oxidation and reduction chemistry. That's it. Thank you for watching.